This question is about diffraction. Let's do part A. A red light of wavelength lambda passes through a single slit. So when you see single slit, it is a diffraction. Okay. Diffraction of width W produces a diffraction pattern on the screen. Now a red light is replaced by green light. Okay. Red light wavelength is lambda and green light wavelength is replaced like 0.75 times lambda. So find the slit width required to keep the diffraction pattern same for both the lights. Okay, that's a question. So what is the question? We have to find out what will be the width when you use green light to have a same diffraction pattern like the red light. Okay, so we know that A, that is the slit width, is a proportional to lambda. Or you know these formulas, that is something like a theta equals n lambda for dark and a theta equals m plus 1 by 2 lambda for bright. Okay, you know these formulas, but forget about that. You know that the slit width is directly proportional to lambda. So let's write this way. So since they used W as the slit width notation, so we can also use the same thing. Let us just use this. W for red is actually proportional to lambda R. Okay, and then W for green is proportional to lambda green. Now what we want is we have to find out WG. So WG divided by WR should be equal to lambda G divided by lambda R. Okay, now it's given that the lambda G, that is the wavelength of the green light, is actually 0.75 times lambda R. Okay, so here it is lambda R. And now we can find out WG, that is the width required for the green light to have a diffraction pattern similar to red one, is WG equals lambda R will go away. You will have 0.75 times WR. So 3 by 4th of the width used for red light should be used for green light. So that's the answer for the part A. Now coming to part B. Find the wavelength of the light that produces first minimum at an angle 30° through a narrow slit of width 0.8 micrometer. So it's given minimum. So we have to use A theta equals n lambda formula. Okay, this is for part B. So theta is given. Okay, so here we have to use sine theta. Okay, sine theta, when the angle is really less than 10°, then only we can use A theta. Otherwise we can use A sine theta equals n lambda. Okay, so theta is given, A is given, n they mentioned it as first minimum, and we have to find out lambda. So it's all the values we can substitute it there. So 0.8 micrometer you can keep it as it is, because the wavelength you can mention in terms of micrometer also. So sine 30° is 1 by 2, n is equal to 1, so lambda you can find out. So lambda equals 0.4 micrometer. Okay, so this is the answer for part B. Now part C, state the formula for the width of the central maximum of the single slit diffraction pattern. Okay, so width of the central maximum, width of central, width. Okay, usually we write width as beta equals 2d lambda divided by A. A is the slit width, D is the distance between the slit and the screen, lambda is the wavelength of the light. So this is the formula. Now, what will be the impact on the width of the central maximum if the whole diffraction apparatus is immersed in a liquid of refractive index n? So here you have to use a concept you learned from the ray optics. You know that the refractive index and the wavelength, they both are inversely proportional. Okay, so if the refractive index is more for water, for some liquid, okay, if it is more, then lambda will be less. If lambda is less, then the central maximum width also will be less. Okay, so that's the answer for the C. Thank you.